to 12. All right. Let's take a look at what's involved in chapter 12. There are three things that we want to cover, so I'm going to just share my screen with you. And I'm going to share this PowerPoint presentation with you here. So we are now getting into what we call comparing multiple proportions and tests of independence. So we've just finished two populations. We did two populations involving means, two populations involving proportions. Now we're going to go to three or more populations involving proportions. We're going to start with proportions first, and then three or more populations involving means. That's when we come to analysis of variance. And then our very last topic is on regression. All right? So let's take a look at three situations that we are interested in. The first one is testing for equality of three or more population proportions. That's a particular test. And to give you an example of that, could be something like this. The same Nova cheddar, what if it had three different markets that it was selling its cheese in? Or it could be four. It doesn't have to be three. It could hypothesize that the proportion or the market share in each of these areas are the same, or that the market share is different. It could hypothesize that. And so in which case, what you would do is you take samples from each of them, and you'd see what percentage of people bought your product versus people who did not buy the product, and then you compare them. So if, for example, in Truro, 30 out of 100 people bought the product, and then in Sydney, 40 out of 100 bought it, and then in Halifax, 60 out of 100 bought it. If you test an equality of proportions, that is equal market share, then 30% is your sample for Truro, 40% is your sample for Sydney, and 60% is your sample for Halifax. That doesn't look like equal proportions to me. So these are the sample values, your observed values, and you would be trying to compare that to some equality of some best estimate of the true population proportion. And then when you compare that, you can see if those three proportions that you just got look like they're equal. and just from the sample that I give you there, 30% does not look like 40%, does not look like 60%. So we have to find a way to actually test whether or not that is the case. So that's the test for equality of proportions for three or more populations. There is a second one that we will get to called test of independence. And test of independence is when we have two categorical variables. Two categorical variables. So say, for example, do you think that gender and political ideology are related? If we could class political ideology into categories like, your left or your center left, right, center right, whatever. If we could create categories, so we have two categorical variables, gender, male, female, political party that you support, the different political parties, and so on. And we want to test whether or not those two things are related or they're independent. And that's used a lot by marketers. Is gender a factor in people's purchasing habits, for example, and so on? Is there some kind of relationship between one's job category and the preference for a particular kind of phone? BlackBerry, which I think has lost significant market share over time, but Samsung, Huawei, name it, Nokia, HTC, Apple, all of those things. So one could say, yeah, no, there's no relationship between one's, employment level versus one's preference for those particular types of phones. But one may very well find that there's some kind of relationship, in which case marketers use that information. So that's a test of independence. The last one is called goodness of fit test. And that's the case where we actually have some kind of hypothesis about the proportions for each of these different populations. So for example, I could say typically 20% of students get an A in stats, 40% get a B, 30% get a C. No, that doesn't sound right. 20, 40, and 30. Yeah, there's still 10% left. And 10% gets the balance, right? So that's the proportions that I believe it to be. And then what I could do is take a sample, break it down, say a sample of 1,000 students who've done stats, and see how many of them got an A, how many of them got a B, how many of them got a C, how many of them got a D, and see whether or not that breakdown fits the distribution I just gave you of 20, 40, 30, and 10, right? So that's called the goodness of fit test. And all of those problems will use something called a chi-squared test. And the chi-squared is a particular distribution that looks something like this. So let me try to show that to you. It looks like the T distribution. It has degrees of freedom. Here it is right here, chi-squared distribution. And we are always interested in the right tail of a chi-squared distribution. So it has degrees of freedom, area in the tail, and a value, a chi-squared value. So that X thing that looks like an X there, we don't call it X, we call it chi. CHI, chi-square. And so let's get into a problem and try to understand this concept through a problem, all right? So if you take your sheet, and we're now going to go to chapter 12 problems. Oh, can't even see that very well, but I'm going to, here we go. Got to share my iPad now with you. Okay. There we go. Now let's try to get a sense of this problem right here. So that's question 5. Question 5 in your textbook if you go in chapter 12. So Kate Saunders, a researcher in the Department of Biology at IPFW University, studied the effect of agricultural contaminants on the streamer fish population in northeastern Indiana. Indiana. That was in 2012. Specially designed traps collected samples of fish at each of 4 stream locations. Our research question was, did the differences in agricultural contaminants found at the 4 locations alter the proportion of the fish by gender? So we had observed frequencies. So did it affect the fish by gender? All right. So it says, focusing on the population of male fish at each location, test the hypothesis that the population proportions are equal for all 4 locations. In other words, find the proportion of male fish for each location, and then we have to then test that against whether or not they're the same, they're equal. Now, if you look at these numbers, let me see, 49 and 41 is 90. So basically we have 49 out of 90. That's more than 50%. We have 44 and 46 is also 90. 49 and 36. I'm just looking at the different locations, the total of male, female. So basically they just collected all the fish and then checked which ones were male, which ones were female. And then you would expect that if the contaminants had no effect on gender, then each of those locations should have pretty much the same, randomly selected, should have more or less the same balance in terms of the gender for the fish, right? So, but we are going to look at the actual data that we found. and see what we're going to do with that. So how do we handle such a problem? So the first thing we got to be able to do is to take the population, that the samples that we have, all right, and then try to figure out if they all should have the same proportion. What is our best estimate of that proportion? All right. So the way in which we'll do that is that we combine all the males, right, in terms of the total number of males across the 4 locations, and then we take the total amount of fish that we have overall and find what proportion of all the fish over all the 4 locations happen to be male. Let's just say that that was about 48%. So now what we will do is we'll take the amount of fish caught at each location, multiplied by that 48% to determine what is the expected, if the proportions are the same, what should we expect in terms of the number of males collected at each location? And if what we expect to collect is very different from what we actually collected, that's evidence that there is some difference between those, all right? So that's how this problem actually works. Okay, so here's what we do. First thing we're going to do with that is we're going to tally all of the male fish and all of the female fish and determine a total. So we get a total over here, and if we add it all up, I'm going to be a little lazy. We get 181 male fish, 167 female fish, 181, 137, 167, sorry, 167 female fish. And so that gives us a total of 348 fish. So out of that total of 348 fish, essentially, our best estimate, if all of them have the same proportion of males, our best estimate should be P bar is 181 over 348. That's what our best estimate should be. And then we could take that best estimate and then multiply it by the sample sizes at each location to determine what proportion of males that we actually had. Well, not proportion, what's the expected number of males, and see if that is different from what we actually had, all right? So the way in which we set up this problem is as follows. I'm just going to clean this bottom part here because I'm going to need it. So gender, male, female, location A, B, C, D, total, and then 49, 41, 44, 46, 49, 36, 39, 44. When we add it up, I've already said 181, 167, 348. And when we add up the totals of the columns, we will get, the first one was 90, okay? 90, 90, 85, 83. So those are the numbers that we have, right? So that's what these frequencies, we refer to those as observed frequencies. These are observed. But if we expect them, all of the locations to have the same amount of fish, this is where we're going to need to essentially determine what the best estimate of the proportion of males should be, and multiply it by the sample size for a location and get that. So in that case, our best estimate is 181 over 348 is the best estimate of the proportion of males for all locations. And then if we multiply that by the 90, it will give us what we expect to have if they all have the same proportion of males. So you'll notice that if I were doing the first one, I would take 181. If I'm going to try to determine for location A, how many males can we expect to find if the proportions are the same? Well, what I do is I use 181 over 348 as my best estimate of the proportion of males overall, and then I multiply it by 90. If I repeat that for the next one, for B, 181 over 348 multiplied by 90 again, and I repeat it again, it would be 181 over 348 multiplied by 85. So that would give me the expected number of fish for each of those locations, right? Because what I've done is I've averaged out all the locations to give me 181 over 348, and now I'm multiplying the samples from each location by that proportion to get my expectation. If you look at that formula, you'll notice what it is that the 181 is the row total. The 348 is what we call the grand total, and the 90 happens to be the total of that column, the column total. So for any cell, we take its row total divided by its grand total, multiplied by the column total. And that gives us the estimate that we're looking for. All right? It turns out that those numbers are 46.81. Now, this has gotten a little bit messy here. So the best thing to do is to clean that up by going to clean page. So again, I'm just going to take the gender, male, female. I'm going to put a little bit of space between them, B, C, D, and totals. Just quickly write that over again. 49, 44, 49 and 39. Then the bottom row is 41, 46, 36, and 44. 41, 36, 41, 46, 36, I believe. The other one is 44. So totals 90, 90, 85, and 83. 90, 90, 85, 83, 348, 181, 167, right? So the row total times the row total, column total over grand total. So this very first one for males in location A would be, so what you could do is you could either repeat this table and put the expected values, or you put them right in brackets next to it. So I'll just put it in brackets next to it. So it would be row total, 181, times the column total, 90, over the grand total, 348. That will give me the very first one, which happens to be 46.81. All right? 46.81. Then we have, if I repeat that, I'll just do one more and I'll just write in the values for you to see. 181 times 90 again, divided by 348. So that will also be 46.81. I'll put it on the side, 46.81. The next one for 49 would be 181, that's the row total, times the column total, which is 85, divided by 348. That will give us for C. And when we calculate that, we get 44.21. And if I repeat that over here, it is 43.17, 43.17. Then if I go to the bottom row, now I'm going to use the 167. So basically, there was 167 female fish out of the 348. So our best estimate of the proportion of female fish would be 167 over 348. Now, if I multiply by 90, it tells me how many female fish that I have in location A. Multiplied by 90, how many female fish in location B I should expect to get. Multiplied by 85, how many female fish in location C I should get, times 83, how many female fish in location D I should get. So I get the following numbers, 43. So I just do one of them for you to see. So it would be 167 times 90 over 348. That gives me 43.19. So that's the 43.19. And then if I repeat that, that's also 43.19. And then for the next one, 40.79. And 39.83. 39.83. So what do we call the ones in brackets? I mentioned to you earlier that the original ones were observed. That's what we observed. 41s observed. These ones in the brackets, we refer to them as expected. Expected frequencies versus observed frequencies. And the idea is, we observe 49, but if the proportion of fish in each location is the same, we expect to see 46.81. Now, the question you'll ask yourself, is 46.81 very different from 49? Maybe it is, maybe it's not. We don't know, all right? And so the thing about it is that we now have to measure whether the expected frequencies are very different from the observed frequencies. So that's where chi-squared comes in. So chi-squared is given by the following formula. Observed frequencies, FO, minus the expected frequencies, FE, squared over FE. And then we add it all up. That's the formula that we use for calculating a chi-squared. So notice that it has no negative values. And of course, the bigger the difference between the observed frequency and the expected frequency, the bigger chi-squared, which pushes us into the right tail of the distribution, because the chi-squared distribution does not have a negative value. It's all based on the square of these differences. So the further apart the expected frequency is from the actual frequency that you observe, the more evidence that you have that there is a difference between those. So we actually need to go ahead and calculate chi-squared as follows for each of those things. We will do, using that formula, we will do 49 minus 46.81 squared over 46.81 plus 44 minus 46.81 squared over 46.81 plus, and if we repeat that, there are what, 8 values for the very last one, which is 44 minus 39.83 squared over 39.83. It turns out that chi-squared is equal to 2.49. I'm doing the calculation before I even set up the problem for you to see how we set it up. It's still the same 5 steps. The only thing that is different is our test statistic has now changed to that formula you just see there, and that we are now using a different distribution, but the same principles apply. So I wanted to concentrate on the concept of essentially calculating expected frequencies and comparing those to observed frequencies. And when those are very different, that is when we say that we cannot accept HO, right? So we're basically assuming in this problem that the proportions are all the same for each location. And if it turns out that the observed frequencies are very different from the expected frequencies, then clearly the proportions are not the same for all locations. So right now our chi-squared is 2.49. We don't know if that's good or bad yet. We will soon find out. I'll come back to this value. So let's set up the problem to see exactly what it looks like. And all those 3 cases that we talked about, goodness of fit test, test of independence, and this one, test of equality of proportions, they are all calculated exactly the same way. It's just that the problem context is a little different. So in this case, typically, we just have a binary situation, male or female, A or not A. We could do a setup where we could look at faculties, and whether or not the students are Canadian, live in Canada, or from abroad. So you have these two possibilities. So that particular problem works in situations where you have a binary situation. Either it is or it isn't. All right, so male or female, it's working or it's not working, etc. And then you could then test for the equality of proportions of one of them. If you're testing for equality of proportions, it don't matter which one of them, as long as if you reject the null hypothesis, then the proportions are not the same for each category, whatever that is. All right, so here's why we set it up. So step 1, we are interested in whether or not the proportions are the same for the different locations. We're focusing on the proportion of male fish at each location, test the hypothesis that the proportions are equal for all 4 locations. So proportion of male fish are equal for all locations versus they're not all the same. All right. So HO, proportions of male fish equal for all locations. That could also have been a question about the market share, but all the locations are the same versus not all the same. So either you bought our cheese or you did not buy our cheese. That's basically the binary situation right there. HA, the proportions differ. That's it. So if the proportions are all the same, we have P1 is equal to P2, equal to P3 is equal to P4, the 4 locations, or we could use PA, PD, PC. Maybe that's a little better, just to be consistent with the problem. PC, PD, they're all the same. HA, at least one proportion is different. I don't know which one. I'm just interested in showing that they're not all the same. So that's the first part, step 1. Step 2, test statistic, which is chi-square. Chi-square is F observed, FE, which is the expected, divided by FE, and we add it all up. So FO, observed frequency, observed count, FE is the expected. Right? And so now Oh, and then we need degrees of freedom. The degrees of freedom is k minus 1, where k represents the number of populations. In this case, we have k is equal to 4 for our problem. All right? Step 3. Decision rule. Remember, once we get the first 3 steps, we're good to go. So chi-squared is actually a skewed-looking distribution that looks something like this. And alpha is always in the tail. It's not alpha divided by 2. So I believe this was 5%. And this is chi-squared critical. The same way we had Z critical or T critical is chi-squared alpha degrees of freedom. So what's our degrees of freedom? DF is k minus 1, which is 4 minus 1, which is 3. Alpha is 5%. So we got to look at 0.053. And let's see what we got for a critical value. All right, let's take a look at the chi-squared distribution. So our degrees of freedom is 3, as you can see here. And then if I look for 5% in the tail, I believe the problem did say 5%, or was it 10%? Let me see. 5%. So 5% in the tail, 3 degrees of freedom is 7.815. That's our critical value, 7.815, right here. Just like you do with the T distribution, that's how it works. Excuse me. And you may recall, we calculated a value of 2.4 something. So definitely we're not going to reject the null hypothesis. All right, so chi-squared critical is chi-squared 0.053 to 7.81, I believe it was. And so if chi-squared observed is greater than or equal to 7.81, reject the null hypothesis. Otherwise, fail to reject. All right. And let's look at our calculation. So if we go back here, we did that calculation. That's the analysis that I did to try to explain the problem to you. So I'm not going to do it all over again. I'm just going to accept this value of 2.49 as the value right here. Okay. So that's step 4. Analysis. So calculated earlier, chi-squared, which is FO minus FE squared over FE, where FE is the row total times the column total divided by the sample size or grand total. So that's how you do that. You find the FE for each of the values, the corresponding. And say, what's its row total? What's its column total? Divided by the grand total. and that will give you FE. Once you do that, you will get 2.49 when you add them all up. If you want to find the p-value, you just simply need to look up 2.49, and I will just tell you what that is without actually changing my screen. If you have your chi-square distribution, what you got to do is just like you do with the t-distribution, you go into 3 degrees of freedom, you're trying to find 2.49, and the 2.49 lies between 10% and 90%. That's the, so it's actually greater than 10%, but less than 90%. So our p-value, like I said, you would handle this very much like a t-distribution. So if you know how to do t-distribution, you could find p-value using chi-squared. So the p-value is the probability of chi-squared greater than or equal to 2.49. And it turns out that that p-value, when you look up the values in the table, is between 0.9 and 0.1. It's greater than 10%, but less than 90%. So as you could see, that is going to be greater than alpha. And of course, our 2.49 is not greater than 7.81. So we will fail to reject the null hypothesis. Step 5, the decision conclusion. So since 2.49 is less than 7.81, or since p-value is greater than 5%, we fail to reject HO. We have insufficient evidence that the proportion of males at each location differ. We have insufficient evidence that the proportion of males differ. But males differ by location. So essentially what that experiment allowed us to do was to test whether or not the chemical contaminants is affecting the gender. So all we need to do is to study one of them. If it's affecting males, and it's affecting females as well too. And so what we do, first of all, is we collect some data. We take samples from each location, see how many males and how many females are in each of those samples. Then we say, let's take the overall number of males, overall number of females. We determine the overall sample size of collected over these 4 locations. And then if we take the number of males and divide it by that sample size, we get the proportion that's males in that overall sample. And then we have also the proportion of females by simply subtracting from 1. So if you now assume in the null hypothesis that the proportion is the same across all locations, you could just use that estimate that you have from that by combining all of the samples, use that estimate as your estimate of what that proportion is. Now all you need to do is to take these estimates and calculate then what number of male fish you expect to see in each of those samples based on that proportion. So now you have an overall proportion for males multiplied by each sample, and you get the expected number of males in each. Then you have the overall proportion that was females multiplied by each sample, and then sample, and you will get the expected frequency for females for each of these samples. Now, is the expected frequency close to the observed frequency? If it's close, then you cannot reject the null hypothesis. If it's far apart, then you got to say, hang on, this is what we expect. This is what we saw. This is very different. right? And so therefore, if you had a large enough difference between them, then you have to reject the null hypothesis. So that's in a nutshell what we're doing here. I mean, another example of that is like if I said to you, 20% of students get an A in stats. Well, actually higher than that, 30-something percent, 35%. Let's say 35% of students get an A in stats. So if you now turn around and take 100 students, and then you observe 15 got an A, right? That's the observed frequency. So you say, but hang on, based on what we know, that 35% gets an A, out of 100, we expect to get 35. Well, 35 is what we expect, 15 is what we observe. That is huge. But is it large enough to say, oh, something is wrong? So we have to measure that. We measure that by chi-square. And then if we get a sufficiently large value for chi-squared, we reject the null hypothesis. So that example I just did is what we call test for the equality of proportions. We could repeat that now for goodness of fit and test of independence. I think that it's a bit, we went through proportions, an introduction to multiple proportions or multiple populations involving proportions, not just two, but two or more, actually three or more. And I would like to stop here. What I will do is that I will continue with two examples, not online, but offline. I will do two examples, one involving test of independence and the other one involving the goodness of fit test, and send that to you very shortly so that you could review it before Monday. Monday, I will just do a quick check to see if you understand the concepts. And if you do, I would like to see if we can move forward to analysis of variance. So basically, I'm trying to move ahead by one class based on our schedule. All right? So please, I'm going to post those two videos on Brightspace rather than YouTube. And then that way, those two topics can be reviewed. Please look at chapter 12, 1 to 3 before Monday, and then go over these examples that I've just done. And you should be good with that, with the particular topic. I have the solutions to those problems in Brightspace so that you could actually check it out yourself as well. All right? But it's always useful to kind of use the one without the solutions, try to see if you understand it, and then do that. Now, in Dr. Lee's problems, he only covers one of those three topics, which is the test for independence. Had we done that, and then we would have finished off with that topic and we could move on to analysis of variance. Analysis of variance for some people is a bit tough. Some people find regression tough, but I think that they're very manageable. But yes, if we were to say, which is the hardest topic, it's probably, for most people, is analysis of variance because it has a lot of computation. But we will kind of do that largely by Excel, because in real life, you're not going to do all these computations. So I want you to understand the concept and then use Excel to actually do the computation for you. All right? So I'm going to stop here. Take a question or two if you have any right now. If you don't, I will bid you good night. And I think somebody has a question or something for me. Okay. All right. Thank you, Eugene. So was that a useful session, you guys? Yeah. Okay, great. So no problem. I will, like I said, do two examples on test of independence, but the computation is exactly the same. It's just the context. As I mentioned to you, the context in terms of independence is when you have two categorical variables and you have 3 or more levels. Well, it doesn't have to be 3 or more levels, but you have multiple levels in each, like political affiliation and gender. Or is there some kind of preference for a particular kind of entertainment and say the faculty that you're in? If you're in business, science, or arts, and then types of entertainment, movies, live music, sports, whatever. So in that case, all we do is we take a big sample and we ask people to make a choice. First of all, what faculty are you in? And then what's your preference for entertainment? Which one of those you like the most? And then you just count how many people who are in science who like sports, how many people in science who like movies, how many people in science who like, and then that table gives you what we call a contingency table. So, and then you do exactly the same calculations, row total, column total, and all of that. I will do it in the example. And then finally, the one on the goodness of fit test, where we now will specify and say, oh, 20% of students get an A, 40% get a B, 30% get a C, 10% get a D, right? So now I specify the distribution, and I will collect data to see if that distribution holds. If the distribution holds, then we say, oh, that's a good fit. If the distribution does not hold, that distribution is not a good fit. And so we're now checking on the basis of those proportions, what do I expect to see if I grab a big sample? How will it break down? So if I now have, say, 1,000 students, and I count how many of them got an A, how many of them got a B, how many of them got a C, how many of them got a D, and those proportions are not lining up with the 20, 30, 20, 40, 30, and 10. If it's not lining up with that, then I have to say, ooh, something is not right about those two things. So that's the other 2 problems that we're going to go over. All right? Cool. Have a good night, folks, and enjoy the rest of your week. Back to SMU, I guess. For those of you who are full-time and those of you who are part-time, have a good working week, okay? All right, take care.